Hello, I hope you're having a good day. In today's video, we'll be analyzing this alternating current circuit, and I'll show you and teach you how to convert two elements that are in parallel, such as this capacitor and this inductor, into an equivalent impedance value we can work with. So how do we begin? Well, we first need to obtain the reactance values of both the capacitor and inductor. How do we do that? Well, we use the formulas we already know. The formulas are capacitor reactance equals 1 divided by 2p times frequency times capacitance, while the inductor reactance equals 2p times frequency times inductance. We've seen this in the previous video. If you want to learn more about this, you can go and check that video. I'll link it in the description. Now the only thing we have to do is to do these operations to obtain the reactance of both the inductor and the capacitor. Let's start with the capacitor. The reactance of the capacitor will equal 1 divided by 2p times frequency. In this case, frequency is 30 Hz times capacitance, which is 15 farads. So we just do these operations. Here, when doing this multiplication, this one, we must be careful and not have the calculator set on degrees, because a common mistake I've seen many people make, a lot of my classmates and myself, in previous years, is having the calculator set on degrees when you actually need to have the calculator set on radians. Why? Because the product of this multiplication, which is p, and the frequency equals angular frequency. And the measurement unit of the angular frequency is radians, so don't make that mistake. 2p times 30 will equal about 188.5 radians. So now we just do this multiplication, and the reactance of the capacitor will be the result of this division. So we do that and obtain this value. Okay, so that's the reactance of the capacitor. Let's move on to the inductor. The reactance of the inductor will be equal to 2p times frequency times inductance. We already did this operation, this multiplication. The value won't change because the frequency is the same. So we can just write here the reactance of the inductor will equal 180.5 radians multiplied by the inductance. So now we just do this multiplication to obtain the reactance of the inductor. So we obtain these two values. Let's write them in the correct way, because this is expressed in ohms. Plus we also need to add the phase angle. So the final values will be 5655 ohms with a phase angle of 90 degrees. I explained in the previous video why the inductor has a phase angle of 90 degrees while the capacitor has a phase angle of minus 90 degrees. Okay, so we have both values. What do we do now? Well, we simply use the formula we always use to obtain the equivalent value of two resistors in parallel. It also applies in this case if we have a capacitor and an inductor. It doesn't matter. So we use the formula. The formula is the equivalent impedance will be equal to 1 divided by 1 also divided by R1 plus 1 divided by R2. In this case, the equivalent impedance will be equal to the same formula. However, in this case, R1 and R2 will be the reactants of the inductor and the capacitor. So now we just need to add the values we actually have. Here we must add the phase angle that these values, these ones have. So they have a phase angle of 0 degrees. This is just to not confuse ourselves. So now we just have to do these divisions. Here we need to subtract the angle when we are dividing them. So we subtract 90 degrees from 0 degrees, which gives us here the value of minus 90 degrees. And here is the same thing. We subtract minus 90 degrees from 0 degrees. When you subtract a negative value, the result will be positive. So we obtain 90 degrees here. Now it's just a matter of doing this addition and adding these two so we can obtain the impedance. Here, because this value is so small, we can just say that the result of this addition will be this. And the phase angle will be 90 degrees because the largest value here is the one with the positive phase angle. So, when you have a situation like this where you are adding a capacitor and an inductor and they both have a negative phase angle and a positive one, the angle that will prevail is the one that has the largest reactance value. So if in this case the capacitor here, which has the minus 90 degrees angle, had a larger value here, the value will be minus 90 degrees. So now the impedance value will just be the result. So now the equivalent impedance will equal this. Remember, here the phase angle is negative because when we are doing divisions with angles, we subtract them. And we can assume that this has an angle of 0. So we just subtract 19 from 0 and get a phase angle of minus 90 degrees. Now we can imagine the circuit as this, where here we have our voltage source, it stays the same. And here we have this impedance value. While here we have our 20 ohms resistor with a phase angle of 0 degrees. Now, if we want to obtain the total impedance of the circuit, we just have to add these two. We know that the way and the formula to obtain the total impedance is adding all the resistors that offer an opposition to the current in a circuit. So we can say that the total impedance will equal this. And now, how do we solve this? Well, this equation is in the polar form, so we can convert it to the rectangular form to obtain the total impedance. So we can say that the total impedance will equal 20 minus and we add the j because this is in the imaginary realm. This is an imaginary number. And why are we subtracting this? Why is it a subtraction instead of an addition? Well, because you can see that the phase angle, the imaginary part, is negative, so we subtract it. And I think we all remember the formula from the previous video, where if we have an equation in this way, we can simply say that the total impedance value will equal the square root of the real part squared plus the imaginary part also squared. So we can express that in this way. Here we can say that since this is a very small value, it will even get smaller when we square it, so we can just get rid of this because it won't make any great or significant difference in the final result. So we can say that the impedance value will equal this. So we remove and cancel the square root with the exponent. The impedance value will equal 20. Remember, we got rid of this because it's such a small number that it won't make any difference. And now we have obtained the total impedance value, but now we have to obtain the phase angle. We do this with the other formula we saw in the previous video, where the angle equals the arctan of the imaginary part divided by the real part. So we can say that the phase angle will equal the arctan of this. Don't forget the negative sign. And we just do this division and obtain the following value. So we just put this in our calculator. Now we have to set the calculator in degrees. Don't forget that. Don't make the mistake of still having the calculators in radians. We are no longer using them. So the phase angle will be this very small value. And with these two values, we can say that the total impedance will equal 20 ohms with a phase angle of minus 0.001 degrees. This means that the capacitance part has a stronger effect on the circuit than the inductive part. Now if we want to find the total current, we just divide the voltage by this value. So the total current will equal 20 volts with a phase angle of 0 divided by 20 ohms with a phase angle of minus 0.001 degrees. So we can say that the total current will equal 1 ampere. Since it's a very small degree, you can just say that the phase angle of the total circuit of the voltage, the impedance, will equal to 0. However, if you like working with very precise numbers, then this is the value. Thank you for watching.